Safety relief valves, design and selection principles, criteria, and configuration guidelines for pressure relief devices and process systems. General design criteria. Relief valves are selected based on standard dimensions and performance categories to ensure consistent application across projects and simplified spare parts management. The following guidelines define baseline specifications. Relief valves should conform to standard sizes as per API 526. Standardization across site should be maximized. Proposed valve sizes should be submitted for approval to reduce spares. Inlet and outlet flanges must be integral to the valve body unless otherwise approved. All flanges must meet ASME B16.5 standards. Flange ratings should correspond to the system pressure classification. Flange rating selection by system class. System class 150, inlet class 300, outlet per API or higher if required. System class 300, inlet class 300, outlet per API or higher if required. System class 600, inlet and outlet class 600. System class 900, inlet and outlet class 900. System class 1500, inlet and outlet class 1500. System class 2500, inlet and outlet class 2500. For large orifice valves, type P and above, and where design pressures exceed standard limits, select the next higher flange class. Outlet flange ratings must match the requirements of the discharge system, open flare, atmosphere, or pressurized system. Steam service valves discharging to atmosphere above 250 degrees Celsius must be of the exposed spring type. Manual lifting devices are only allowed for steam, hot water, and air services. Test rods are not permitted in any relief valve assembly. Shaft-specific selection criteria: spring-loaded relief valves, non-balanced, use when built-up back pressure does not exceed the allowable overpressure. Variable back pressure is manageable without affecting valve opening pressure. Constant back pressure exists. Spring must be sized to compensate. Must have closed bonnets if connected to closed discharge systems. Open quote, caution. Use of non-balanced valves in systems where other valves may simultaneously relieve can increase back pressure beyond limits. Consider balanced or derated valves in such cases. Close quote. Balanced bellows relief valves use when built-up back pressure exceeds limits for non-balanced types. Back pressure is less than 65%, preferably 50% of set pressure. Bellows are vented continuously and routed to safe areas. Suitable corrosion-resistant bellows material is required. Auxiliary balancing piston may be necessary if freezing or leakage risk exists. Open quote, avoid use in freezing environments, reciprocating compressor discharge, or fouling coking services where bellows may become damaged or blocked. Close quote. Pilot-operated relief valves use in clean services when the inlet pressure drop exceeds 3% of the set pressure. Superior leak tightness is required due to soft seat design. High back pressure, 50 to 70% of set pressure, must be tolerated. Higher set pressure and compact size is needed for large capacity relief. Margin between system op and set pressure is less than 10%. Design considerations. Non-flowing type pilot valve is mandatory to prevent debris ingress. No low points in sensing lines. Avoid hydrate or wax formation. All sensing lines must be heat traced and insulated if blockage risk exists. Filters should not be installed in pilot sensing lines. Air-assisted relief valves used to reduce the operating margin between set pressure and MOP. Incorporate a pneumatic actuator for enhanced sealing near set pressure. 3 configurations exist. 1. Opening assist mode. Spring set at 105% of design pressure. Valve opens reliably without instrumentation input. 2. Supplemental load mode. Spring set at 100% of design pressure. Instrumentation initiates opening. Failsafe open at 110% of set pressure. 3. Combined mode. Actuator augments a 100% spring setting. Allows margin reduction while maintaining redundancy. Open quote, use of these valves may require special approval and instrumentation reliability studies. Close quote. STAR thermal expansion relief valves, TERVs, used to protect against pressure buildup in blocked-in piping due to thermal expansion. Design standards, standard size 25 mm by the 25 mm flange, minimum orifice 0.71 cm squatters. Threaded connections permitted only on bronze valves and only for water service. One-piece body and bonnet is preferred. Screw connections not allowed. This structure establishes the foundation for safe and appropriate selection of safety relief valves based on application, pressure regimes, material compatibility, and operational contingencies. Each type has specific conditions under which it provides optimal performance, and careful adherence to these criteria ensures long-term integrity and safety of pressurized systems. Non-balanced spring-loaded relief valves. Direct-acting simplicity for low back pressure applications. Non-balanced spring-loaded relief valves are the standard choice for most general service applications, offering a straightforward and reliable mechanism for pressure protection. They operate by using a mechanical spring to oppose system pressure on the valve disc. When system pressure exceeds the calibrated set pressure, the spring compresses, the disc lifts, and fluid is vented. When pressure falls below the reseating threshold, the valve closes automatically. Primary application guidelines. Suitable for installations where built-up back pressure remains low and does not interfere with valve performance. Ideal in systems that relieve to atmosphere, flare headers, or low-pressure collection systems. Typically applied when the accumulated pressure, set pressure, plus allowable overpressure is not exceeded by back pressure effects. Back pressure and valve performance. Built-up back pressure refers to the resistance created in the discharge line once the valve opens. In non-balanced valves, this back pressure acts against the spring force, potentially preventing full lift or causing early closure. When constant back pressure exists, the valve spring must be selected and calibrated to compensate for this constant offset. The spring is set for the difference between the set pressure and the constant back pressure. Design limitations and cautions. These valves are not suitable for systems where multiple relief valves may open simultaneously, generating variable back pressure that could prevent a valve from reaching full lift, cause delayed or failed opening in high-pressure scenarios. For systems with potential relief valve interaction or shared discharge headers, use of balance-type valves or conservative pressure settings should be evaluated. Closed bonnet designs are mandatory when discharging into closed systems to prevent process fluid from entering the spring housing. Material and maintenance notes. These valves have simpler construction and fewer components compared to balanced or pilot-operated types, making them easier to maintain. The absence of bellows or pilots minimizes sensitivity to fouling or thermal cycling. However, they may exhibit greater wear or instability if subjected to fluctuating or excessive back pressure. Regulatory and operational considerations. In jurisdictions where pressure equipment regulations are strict, careful documentation of allowable overpressure and system dynamics is essential to justify the use of non-balanced valves. Redundant relief valves or differentiated set pressures may be used to ensure that no valve is exposed to adverse back pressure when multiple valves are relieving in parallel. Summary. Non-balanced spring-loaded relief valves provide a rugged, cost-effective solution for overpressure protection in clean, stable systems with predictable back pressure behavior. When properly applied and sized, they offer rapid response and repeatable operation. However, their simplicity must be matched with a clear understanding of system dynamics, back pressure limits, and discharge configurations to ensure safe and reliable performance. Balance type relief valves. Pressure stable relief for variable and elevated back pressure conditions. Balanced relief valves are engineered to maintain accurate and repeatable performance even when significant or fluctuating back pressure exists in the discharge system. By incorporating a bellows or auxiliary balancing piston into the valve design, the effects of downstream pressure on the opening and closing forces are effectively neutralized. This ensures that the valve set pressure and lift characteristics remain stable, regardless of back pressure variations. When to use balanced relief valves. Required when built-up back pressure exceeds allowable levels for non-balanced valves. Mandatory in systems where back pressure exceeds 10% of set pressure, especially complex header systems with multiple valves. Closed discharge systems with elevated or varying downstream pressure must be selected when stable valve performance is critical and back pressure exceeds 25% of set pressure. Performance parameters and pressure limits. Balanced valves can tolerate back pressures up to 65% of set pressure in general use. 50% or lower preferred for optimal longevity and margin. If back pressure exceeds 25% of set pressure, the valve manufacturer must provide validated test data demonstrating adequate flow and lift. Confirm performance under actual system-specific pressure profiles. Bellows design and safety features. Metal bellows assembly compensates for the effect of back pressure on the disc. The bonnet is vented continuously to atmosphere or to a safe area to prevent pressure buildup behind the bellows. Provide an escape path for process fluid in case of bellows failure. Bonnet vent lines must be routed to a safe location, protected from ingress, freezing, or blockage. Open quote, if routing to atmosphere is not feasible or creates a hazard, e.g. due to toxicity or freezing, consider using an auxiliary balancing piston instead of a bellows. Close quote. Material selection and corrosion considerations. Bellows material must be corrosion resistant to the process medium. In cases where no suitably resistant material is available, auxiliary piston design should be considered. If fluid ingress into the bonnet vent is likely and freezing is a concern. Balanced bellows valves should be avoided. Alternatives such as pilot-operated relief valves with internally heated pilots are preferred. Service-specific restrictions. Balanced bellows valves should not be used in reciprocating compressor discharges. Vibrations and pressure pulsations can cause fatigue cracking in bellows. Coking or fouling services, accumulation within the bellows chamber can lead to mechanical blockage, compromising movement. Advantages over non-balanced valves. Set pressure remains accurate regardless of back pressure changes. Allows use of standard spring designs even in pressurized discharge headers. Reduces potential for chatter or instability due to back pressure surges. Installation and maintenance notes. Bonnet vent lines must remain free of obstructions, ice, or debris. Routine inspection should include bellows integrity checks, monitoring for vent leakage, which may indicate bellows failure. A leakage detection system can be installed at the vent to alert operators to bellows rupture. Summary: balance type relief valves offer enhanced performance in systems subject to high or variable back pressure. By neutralizing the effects of downstream pressure on valve operation, they provide more reliable and predictable relief behavior than non-balanced types. However, their successful application depends on careful attention to vent routing, bellows material compatibility, and service conditions that could degrade or obstruct the balancing mechanism. In environments where freezing, vibration, or fouling is present, alternative solutions such as pilot-operated or auxiliary piston designs should be considered. Sharp pilot-operated relief valves. Precision relief under tight margins, high back pressure, and clean process conditions. Pilot-operated relief valves are advanced pressure relief devices that use a separate pilot valve to control the opening of the main valve. Unlike direct-acting spring-loaded valves, the main valve in a PORV remains closed under system pressure and opens only when the pilot valve vents the dome, the space above the main piston or diaphragm. This design allows for higher set pressure stability, minimal leakage, and superior back pressure tolerance, making PORVs ideal for high pressure, high capacity, and tight margin operations in clean services. Key applications and suitability. Pilot-operated valves are preferred when tight operating margins exist between maximum operating pressure, MOP, and relief valve set pressure, typically 10%. High back pressure conditions are expected, typically 50 to 70% of set pressure. Superior sealing is required to minimize leakage and fugitive emissions. Large flow capacity is needed without the bulk of a large spring-loaded valve. Longer stroke and high lift requirements exceed the capabilities of spring-loaded valves. Functional advantages. Soft seat sealing provides excellent leak tightness, reducing loss of process fluids and emissions. Compact size and lower weight compared to large spring-loaded valves at equivalent capacities. Set pressure accuracy remains stable even under significant per-drop conditions between protected equipment and the relief inlet. Allows a closer approach to the system's MOP, optimizing equipment operation and reducing unnecessary relief events. Offers a higher positive closing force, minimizing the risk of chatter at low overpressure conditions. Design characteristics. Non-flowing pilot valves are mandatory. Once the main valve opens, no process fluid should pass through the pilot circuit. The pilot sensing line must tap as close to the protected equipment as possible to avoid signal lag or pressure drop. The system must be free of contaminants, as even minor fouling in the pilot or sensing line can compromise operation. Installation guidelines. Sensing lines must be short, direct, and free from low points where liquids could collect. Heat traced and insulated in environments prone to freezing or hydrate formation. Sized to prevent delay or dampening of pressure signals. Blockage prevention. Avoid filters in the sensing line. They can introduce restriction and risk of plugging. All exposed pilot components should be evaluated for wax, ice, hydrate, or solid contamination risk. Operational constraints and considerations. Not suitable for dirty or fouling services where pilot ports or sensing lines may clog. Instrument air or control power may be needed for some configurations, e.g., air reset or remote venting. Vibration-sensitive installations may require secure mounting or flexible sensing line supports. In case of pilot or sensing line failure, ensure the main valve still opens under maximum pressure conditions. Special design scenarios. Pilot-operated relief valves are particularly advantageous in systems with large inlet pressure drops, i.e. 3% of set pressure, as pilot placement compensates for signal loss. High-pressure gas compressors, where discharge lines experience large pressure swings and capacity demands. Critical relief systems, where standard spring-loaded valves may not reseat accurately or may experience chatter. Redundancy and reliability measures. Consider dual pilots or instrumentation alarms on sensing line blockage or temperature drops in critical services. Ensure testing and commissioning routines validate pilot opening under simulated process conditions. Some PORVs include internal heaters or traceable housings to mitigate freezing risks. Summary: pilot-operated relief valves provide a refined, high-performance solution where traditional spring-loaded valves fall short, particularly in high-capacity, tight margin, or high back pressure environments. Their superior sealing, accurate set pressure control, and compact footprint make them a compelling choice for clean, stable services. However, their reliability depends on meticulous design and maintenance of the pilot and sensing circuits, making them best suited to clean, well-controlled process conditions with minimal risk of contamination or blockage. Air-assisted relief valves enhance sealing and reduced margin through pneumatic supplementation. Air-assisted relief valves are a hybrid design that combines the simplicity of spring-loaded valves with the precision of instrumentation-assisted actuation. These valves incorporate a pneumatic actuator, typically a diaphragm or piston type, that applies additional closing force near the valve's set pressure. This supplemental load increases sealing reliability, reduces premature lift, and allows the set pressure to be approached more closely during normal operations. Used selectively in critical services, air-assisted valves are especially valuable in tight margin systems where the difference between the maximum operating pressure, MOP, and the valve set pressure is limited to as little as 5%. Principles of operation. A spring-loaded relief valve is equipped with a pneumatic actuator that provides supplemental downward force near set pressure, enhancing sealing, assisted opening force at the set point, ensuring sharp and timely response. The actuator is controlled via a dedicated air or instrument gas line, typically integrated with the system's control logic or independent safety instrumentation. Application scenarios. Air-assisted relief valves are preferred when operating pressure is close to the set pressure with only 5% margin. High process reliability is needed without sacrificing safety. Sealing performance must be enhanced without resorting to soft seats. The relief valve must open sharply at precise set pressure to minimize risk to equipment. Design configurations. There are three primary modes of actuator operation. 1. Opening assist mode. Actuator applies an opening force at set pressure. Spring is preloaded to 105% of design pressure. Valve opens reliably at 105% of pressure without relying on instrumentation. Fully mechanical safeguard. 2. Supplemental load mode. Actuator holds the valve tightly closed up to 100% of set pressure. Valve opens via signal from the instrumentation. In the event of instrument failure, the valve still opens at 110% of set pressure due to calibrated spring. Ideal for integrated control systems with diagnostic reliability. 3. Combined mode, actuator both suppresses premature lift and enhances opening force. Spring is set to 100% of set pressure with supplemental air load. Balanced approach with redundancy in case of actuator or signal fault. Performance benefits. Reduced operating margin, as low as 5%, allows process units to run closer to design limits, improving efficiency. Superior reseating accuracy and minimized leakage in sensitive or volatile services. Enhanced resistance to chatter, especially in gas services with fluctuating flow rates. Instrumentation and reliability considerations. Instrumentation reliability is critical to overall valve performance. In all modes, fail-safe design ensures the valve will still relieve pressure under mechanical spring action if pneumatic systems fail. Redundancy and interlock should be incorporated in safety-critical systems with diagnostics for actuator performance and pressure supply integrity. Pneumatic supply must be dry and clean to prevent actuator fouling or freezing. Fail-safe vented, ensuring actuator release during emergency shutdown. Regulatory and code compliance. Air-assisted relief valves are not defined in most pressure vessel codes, e.g. ASME Section 8. Their use may require approval from local authorities or independent inspection bodies, compliance with Instrumented Pressure Protection System (IPPS) methodologies. Open quote, selection and design must be aligned with recognized risk assessment and HAZOP review processes to validate integrity and fault tolerance. Close quote. Manufacturer responsibility. The relief valve manufacturer is fully accountable for the performance and integrity of the complete assembly, valve body, spring, actuator, accessories, or control interface. Assembly must be tested and validated as a unified system with certification for pressuring lifting accuracy and sealing characteristics. Summary: air-assisted relief valves bridge the gap between mechanical spring-loaded devices and instrument-controlled systems. They enable high-precision pressure protection with minimal margin, especially suited to modern, high-performance processing environments. However, their benefits come with a dependency on pneumatic supply and instrumentation integrity. Careful integration, documentation, and approval processes are essential to ensuring that these valves perform as intended under all operational and fault conditions. HAZOP thermal expansion relief valves, TERVs, localized overpressure protection for blocked-in liquid systems. Thermal expansion relief valves are specialized pressure protection devices designed to relieve overpressure caused by thermal expansion of liquids trapped in isolated piping segments. Even modest temperature increases can generate substantial pressure in incompressible fluids, leading to potential rupture or joint failure. TERVs provide a compact, automatic, and maintenance-free solution to this risk by safely discharging small volumes of liquid when pressure exceeds the safe limit. Application scope. Mandatory in all blocked-in liquid piping systems where temperature rise is possible due to solar heating, exposed pipe runs, adjacent hot process lines, inadvertent equipment startup, typically used in pump discharge lines with isolation valves, heat exchanger bypasses, closed-loop utility systems, jacketed vessels and pipelines, serves local targeted protection rather than plant-wide safety relief. Design characteristics. Standard TERV size for piping systems, a 25 mm by 25 mm flanged body, minimum orifice area of 0.71 centisquimeters to accommodate slow but forceful expansion. Compact construction allows installation on small bore lines without requiring support modifications. Low flow capacity, as the relieved liquid volume is minimal, but the pressure rise is significant and rapid. Material and connection requirements. Flange body design is standard for process service. Threaded pipe connections are permitted only for bronze-bodied TERVs and solely for water service. One-piece body and bonnet design is preferred to eliminate leak paths. Screwed bonnet connections are not permitted for process safety reasons. Integral casting or welded assembly ensures integrity under thermal cycling. Installation guidelines. Must be installed at the highest point of trapped liquid segments to ensure vapor or pressure accumulations vent correctly, prevent hydraulic lock or undetected overpressure, should discharge to a safe atmospheric drain or sealed liquid recovery system not connected to pressurized headers or flare systems. Open quote, where freezing is a concern, the discharge line should be heat traced and insulated or designed with freeze-resistant drain traps. Close quote. Operational features. TURVs operate without external power or signal, purely mechanical actuation, typically not designed to reclose perfectly tightly after multiple actuations, considered sacrificial in some applications. No lifting mechanism or diagnostic instrumentation is required due to simplicity. Inspection and maintenance notes. TURVs should be visually inspected periodically for blockage, corrosion, or freezing at the discharge outlet, leakage indicating repeated activations or internal wear. Consider replacement during routine maintenance if signs of mechanical degradation or corrosion are present. Code and compliance considerations. Though not governed by the same sizing codes as main relief valves, e.g. ASME, API, TURVs should be clearly marked for thermal expansion protection use only. Tagged and logged in the relief valve register. Designed and installed in accordance with internal piping and mechanical standards. Summary. Thermal expansion relief valves are a critical safeguard against localized overpressure in liquid-filled blocked-in systems. Their function is often overlooked during design, yet their presence can prevent catastrophic failures due to simple thermal effects. By ensuring correct sizing, strategic placement, and proper material selection, TURVs provide passive, high-integrity protection in process and utility applications where thermal expansion is a hidden but persistent risk. Relief valve specifications. Material integrity, standards compliance, and service-specific enhancements for pressure safety valves. Relief valve specifications encompass the material, design, construction, and certification criteria that ensure consistent performance across various pressure relief applications. These specifications not only define the minimum technical requirements for reliable operation, but also embed compatibility with fluid properties, temperature extremes, corrosion risks, and international standards. General design and material standards. All relief valves must conform to internationally recognized codes. API 526 for flange steel pressure relief valves, AHAN for power boiler service, ASME 4 for heating boiler service, ASME 8 for unfired pressure vessels. Valve components shall be manufactured using material grades specified on the approved project requisition. The spring component must be specially treated to resist general corrosion in moist or chemically active environments, sulfide stress corrosion cracking SSCC in sour or H2S rich surfaces. Spring coating and embrittlement protection. Springs must be coated to enhance longevity and corrosion resistance. Cadmium and zinc coatings are prohibited due to hydrogen embrittlement risk during galvanizing, liquid metal embrittlement during high temperature service. Aluminum-based coatings or other approved alternatives may be used for enhanced protective layering. Additional requirements for specific services. Oxygen and high-pressure air service. Relief valves intended for gaseous oxygen or air service above 50 barg must meet additional cleanliness, safety, and design requirements. Key provisions include special cleaning procedures to remove oil, grease, and hydrocarbons, use of non-reactive materials in flow path and sealing elements, packaging and shipping with strict contamination controls, clearly marked identifications such as suitable for oxygen service. Open quote, valves for oxygen service must be handled, stored, and installed with extreme care to prevent combustion hazards due to contamination. Close quote. Wet hydrogen sulfide H2S service. All materials in contact with process fluids must comply with sour service standards. ISO 15156 for oil and gas production systems, gas sweetening, and H2S injection. NAC MR 0103 for refinery, LNG, and chemical plant applications. Key material considerations: resistance to sulfide stress cracking, selection of low hardness, qualified heat-treated steels, post-weld heat treatment, PWHT, as necessary for weld integrity. Relief valves must be documented and traceable to prove full compliance with these standards. Service compatibility and material pairing. The full wetted parts of the valve, seat, disc, nozzle, and trim must be compatible with process media properties, e.g. corrosivity, abrasiveness, operating and relief temperatures, pressure cycling, or pulsing, particularly in reciprocating compressor services, Material selection must consider both design, operating envelope, and emergency relief conditions, including fire exposure or thermal cycling. Summary relief valve specifications govern more than just dimension and pressure class. They define the heart of pressure protection by ensuring that valves are built to survive the chemical, thermal, and mechanical realities of their environment. By enforcing internationally recognized construction codes, corrosion-resistant materials, and service-specific customizations, the specification process ensures that every relief valve deployed contributes to both operational safety and system reliability.